Okay. All right. Just a reminder to please turn in homework number 4, and you have available then certainly don't want you to stay idle. You then have available homework number 5 for a week from today on 2 sections. So we're on section 15.5, and we talked about the last time the chain rule. And that really, if we use those tree diagrams, basically the chain rule is pretty just kind of rote to do it. So, you know, we looked at the tree diagram. Oops, diagram, gosh. All right, the last thing we want to cover, and we did several examples then. So the last thing we want to cover in this section is implicit differentiation. With the formulas, with what we've done previously, we very nicely had Z on one side of the equation. Like the one example we had, Z is equal to e to the x sine y, and we had then x is equal to st squared, y is equal to s squared t, and basically Z was isolated right there on one side. Okay. But sometimes things just don't work out so nicely like that. So let me give you an example of that kind of situation. So here we are given x cubed plus y cubed plus z cubed plus 6 times x times y times z equal 1. And now this is where z is our function of both x and y. Okay. Now if you look at this, you see that z is here and z is there, and there's no way algebraically that we can just isolate z on all by itself with nothing else on one side of the equation. Okay. So what we want to find is we want to find delta z, delta x, and delta z, delta y, right? Now, in the textbook, they give you explicit formulas for these, and the problem is formulas are things that you have to memorize, basically, and you really don't need those explicit formulas in order to do this. Okay, you've done implicit differentiation before, you had some in the homework, and basically we go through the same process here with this without resorting to those formulas. So let's start with delta z, delta x, and just remind ourselves that y is going to be considered constant here when we do this process. Okay, so we basically just go term by term. All right. Oops, wait a minute. I have something. What's going on? Oh, okay. Rockwood has a fire drill right now, which means, I wonder if they have a fire drill. That means that both the schools have a fire drill. Probably everybody. I don't know. But anyway, at least one of the schools is. Yeah, okay. So at least I know that means Lafayette is now doing a fire drill. Okay. Oh, well, all right. I post everything online, although the recording last time, I'm having trouble with it, so, but I'm trying to get it on there. All right, so we go term by term with this thing, and we remember all the time that y is being treated like a constant. Okay, so we're doing the derivative, so derivative with respect to x. So that first term, x cubed, just becomes 3x squared. Now the second term, we're going to remember y is a constant, so that term just disappears, goes to 0. Then we go to the third term, z cubed. Well, we just do the chain rule. We bring down our 3z squared, but remember we have to complete it with the chain rule, so we're going to then have dz dx behind it, chain rule. And now we go to this term here. Okay, yes? Because you've got to keep in mind which variable I'm treating like a constant and which I'm not. Now this one, now we're doing the derivative with respect to x. So if I did the change, so for the first term, let's look at this. Okay, x cubed. Do the derivative of that, that's 3x squared. Now technically, if I did the chain rule with respect to x, I'd be multiplying it by dx dx, which is just equal to 1, all right? And we don't even think about doing that. The second term, I'm remembering that y is a constant, goes away. But here, we've got to complete that dz dx. I've got to do my inner function is that z. I've got to do that derivative with respect to x. I don't know if that helped or not. Now let's look, we've got this last term, 6xyz. All right, now, y is a constant, but we have x is our variable, z of course is our variable. So one way we can do this is obviously 6 is a constant, y is a constant, so let me just put those down. And then let me put some parentheses here, and then what I have to get the derivative of is x times z. All right? So for this now, we need to use the product rule. X is a variable, z is a variable. So we have to do the product rule, all inside that parentheses. Okay, so we can do x times the derivative of z, so that's x dz dx. Plus, then the derivative of x is 1, and then we have z, so the second function, product rule. All right, equals 1, of course, is going to go to 0. All right, now, once we've successfully done that, Jen, are we okay with that product rule with that? We've got two variables. All right. Then it's a matter of combining all the terms that have the dz dx. All right. So let's do a little. So let's see. 3x squared. I'm going to have to do a little intermediate distributing here first. Plus 3z squared dz dx. Plus, now let's distribute here. I have 6xy times dz dx plus 6yz equal to 0. So I've done that. And then now I can combine the terms that have the dz dx in it. So dz dx times parentheses, well, we've got 3z squared, and we've got 6xy. Now the other stuff, the terms that don't have the dz dx, I need to move that all over to the other side of the equation. So I've got to subtract 3x squared. I've got to subtract 6yz. All right? So that gives us minus 3x squared minus 6yz. All right, and then my last step is just to divide by the what's multiplying the dz dx. So dz dx is equal to, it's isolated now, it's equal to minus 3x squared minus 6yz all over this other thing, 3z squared plus 6xy. Okay. And then this is certainly a correct answer. It's not a simplified answer, though, because if you look here, all the constants are multiples of 3. So I'm just going to divide out a 3 here and come up with minus x squared minus 2yz over z squared plus 2xy. And that's my simplified final answer then. Okay, that was 1/2 of the problem, dz dx. So let's just, for the heck of it, let's do the other half of it and get dz dy. Now, I like to mark on my paper because I tend to sometimes get distracted. So I like to mark on there what's being treated as a constant, because I sometimes need all the help that I can get. So I'm going to mark here x as constant. All right. Okay, again, we're going to go term by term with this. And now our first term, x to the third, that's going to go away to 0. Then we go to our y to the third, and we're doing the derivative with respect to y. So that just becomes 3y squared. Okay. And now it's time to do the chain rule again with the z to the third. We do the derivative, get 3z squared, and then finish it with the chain rule with dz dy. And then we look here at this last term. Now this term, x is a constant, so we can, here it's we can treat it as 6x times yz. So we're going to keep the 6x right there, and then again, we're going to use the product rule to get the yz derivative. Okay, so that's going to be y, derivative of z with respect to y, plus derivative of y is 1 times the z. This is almost like a mirror image of this previous problem. And that all equals 0 because we have a 1 there. All right. Then, again, I'm going to distribute and then combine the dz dy. So that's 3y squared plus 3z squared dz dy. Plus, let's distribute 6xy dz dy plus 6x times z equals 0. And now combine. dz dy is going to be multiplying what? 3z squared and 6xy. Let's get the other stuff on the other side. We have a 3y squared, and we also have a 6xz, minus 6xz. All right? And then we divide, and we're almost done. dz dy then is minus 3y squared minus 6xz all over 3z squared plus 6xy. And again, that's a correct answer, but again, it can be simplified by dividing out a 3 from each term. Minus y squared minus 2xz over z squared plus 2xy. Okay. So if you actually are looking at the textbook, you see these formulas here. You can, if you just go through these steps, you don't have to be memorizing these formulas. Okay. The last thing then for this section on the chain rule, I don't think that section's too bad. What we're going to move on to next then is kind of a generalization, in a sense, of these partial derivatives. And I've got a couple of things that I can show you to help with the process. But what this is called, this section is about what's called directional derivatives. Oops. All right. Let's see, let's first start out with this. Okay, let's look at z as a function of x and y. Now, when we were doing the derivative with respect to x, that was really looking at the rate of change in the x direction, okay? So therefore, fx, that was the rate of change in the x direction, and fy was the rate of change in the y direction. All right, okay. Now, another way of looking at that, okay, the rate of change in the x direction, well, what in the x direction, let's just actually look here at here's x, here's y, and we're going up here to z. So we're talking about the rate of change in the x direction. What's a unit vector that points in that x direction? Just looking at two components, x and y component, of a unit vector that goes in that direction. 1, 0, right. 1, 0 with those brackets around it, okay? So that's really the rate of change if we're pointing in the direction of that vector. And then for the y direction, a unit vector going in the y direction is going to be 0, 1, all right? So that would be the rate of change if we're pointing in the direction of that particular vector, all right? Now, what we have here with directional derivatives is that we don't just confine ourselves to those two particular unit vectors as directions. We can look at any unit vector pointing in any direction in that xy plane. So, suppose we want to find the rate of change of z equal a function of x and y in the direction of an arbitrary unit vector AB. Oh, and let's call that U equals AB. Because I want to emphasize that in the book they talk strictly about unit vectors for these directional derivatives. Okay. Now, let's look at, let's see, tangent lines. All right. Do I have something like that? I don't see that. Let me try to draw something here. It's not anything. Yeah. Yeah, here it is. Sorry, folks. If I want to make an excuse for myself, we were powerless, but there was no electricity all last evening after 5 o'clock. All right. I found it here. All right. So here we've got this surface. That's this gray area. The surface here. Here's our x, y, and z axis. And say we're looking at this. Want to look at this particular point that's on the surface of the a point on the surface itself. And let's say we're for whatever reason we're interested in the rate of change as we're going in this direction here on the xy plane. Okay, so that's our unit vector there, u. And so basically we can look at this as we can take that line and we can extend a vertical plane all the way up and down with that particular vector in it. And as a result, when we get to our surface, we cut a curve in our surface when that vertical vector hits the surface, vertical plane hits the surface. And so that gives us a curve, and then that curve, as we've seen before, that curve there gives us a tangent line that just brushes the curve. And then the slope of that tangent line is going to be the value of that particular directional derivative, all right? So slope of the tangent line, well, let's say gives us, let me put it this way, gives us the rate of change in the u direction. Okay, all right. All right. Now, this is this rate of change here, this is called the directional, this is the directional derivative. So the derivative, I'll do this. The derivative that we're talking about involved here, the derivative involved with this type of rate of change, with this type of rate of change, is called the directional derivative. Okay. All right. Now let me give you the formal what? We can't see anything that you're currently doing. Okay. Can you do what now? Can you open the window? Well, can you open the blind? Certainly. I don't think you can open the windows, though. Okay, good, Harry. I'm glad everything is okay. That freaks me out when I see that we can't see anything that you're doing. Let me put this, by the way. Don't forget to turn in homework. And homework number 5 is due next Friday. All right. All righty. Okay. So let's get the formal definition here that they give in the book of this directional derivative. Okay. The directional derivative of fxy at the point x naught, y naught, we always have to talk about what direction, in the direction of a unit vector. Again, I want to underline unit vector u equaling a comma b is the following. Now, the way that we write this here is we put a capital D for derivative, and then below here as a subscript, we put our unit vector, whatever our unit vector is, and then we put our function here, and then I'm going to put the point that we're talking about, x naught, y naught. So this is notation that I want you to become familiar with for just denoting a directional derivative. And what it equals formally is this: the limit as little h approaches 0 of the following. We take our function and we first of all look at the value we start with the x naught value, we add whatever that h is to the x, and then we put the x component of our unit vector, and then we have our y naught plus h times the y coordinate of the unit vector, and then we subtract the function at x naught, y naught. Oops, that ran out of space there. So basically, it's the difference of the function moving along that line. So we increase x by HA, we increase y by HB. And this is all divided by that difference h. And we take the limit as h goes to 0. Now, with that said, you're not going to be having to formally use that definition as far as computing anything, okay? But that's what the formal definition is. Okay. Now, again, I'm going to repeat here what I had stated earlier. Note that for fx, the u vector is equal to 1, 0, and for fy, the unit vector is 0, 1. Okay. Now, the next thing I put here is what you are going to use in order to calculate these directional derivatives. And this is the theorem here. So theorem, we're assuming that our function of two variables, x and y, is differentiable. And the functions that we're going to be looking at are going to be all good functions that it is differentiable. If fxy is a differentiable function, then its directional derivative in the direction of u equal to ab, again, this is a unit vector, is, okay, d, capital D, u of our function, fxy, is equal to this. It's going to be the a component, a, that number a, times the fx, the partial derivative with respect to x of our function, plus the y component of the unit vector times the partial derivative with respect to y. Okay. This right here, asterisk, is what you're going to be using in homework, etc., on calculating directional derivatives. So notice that the only thing different here is that we have to be multiplying the fx and the fy by numbers, okay? Now there's another way of writing this. Another way I can write that very same expression on the left is this. Let's look at this. Fx, fy as a vector dot a comma b. Now this is the dot product. Remember how we calculated dot product? We just multiply together the corresponding components. So the dot product here is fx times a, which is the first component I have up here, plus multiplying the second components together, fy times b. So this is another way of denoting the directional derivative. Okay. Now, remember this a comma b is a unit vector. I know I keep repeating that, but I want to make sure that we understand that. All right. Let's look here. Let's just look at the xy plane here. So let's call, this is u, of course. If we have this unit vector, now this unit vector can be, let's just put its tail here at the origin, all right? I mean, it can be anything. It can be here, it can be there, here, any kind of direction there with the origin. Well, let's just look at one to single one out. So let's say that this here is our unit vector u. Well, we can look here at the angle that it makes with the x-axis here. And let's say the angle that it makes, we're going to call it theta. So this is the angle with the positive x-axis. All right. Now, if we have that angle, I then can get the two components of u, the x component and the y component. So remember, we can just kind of let me actually enlarge this because I'm getting too small where you can't see what the heck I'm writing. So here's our u. It has an angle theta here. So to get the two x and y components of this, I can just basically drop a vertical dotted line down to the x-axis. And remember, the length of this thing is 1, length 1. So the x part of it I can represent as the cosine of the angle theta. And the y part of it is going to be the sine of the angle theta. So my u, then, the components are going to be cosine of theta, sine of theta. And that's certainly a unit vector. The magnitude is equal to 1. Okay? Because we know the magnitude is the square root of the squares, sum of the squares, and so that is equal to 1. All right. So another way, then, of looking at this directional derivative, we've said here, directional derivative in the u direction of our function. We have said one way of writing it is fx, fy, dot a comma b. Well, I can write the a comma b as cosine and sine. So this is fx, fy, dot cosine of theta, sine of theta, like that. Okay, right? And that's our u. So let's look at an example here of doing this. So example. Okay, let's say our fxy is equal to x to the third minus 3xy plus 4y squared. And we're asked to find this. Find d, capital D, directional derivative in the u direction of f, where, so what in the world is the u direction? Where we're saying where this angle theta is equal to pi over 6, which of course we know is 30 degrees. Okay. So basically we're gonna use our formula up here and figure it out. So obviously, to get the directional derivatives, you have to get fx and fy. That's just part of it. So let's get fx. So that means I'm going to write it down. That means y is a constant for that function. And go term by term. So x to the third is going to become 3x squared. My middle term is going to become what? Minus 3y, yes. The y is going to stick, oops, and I was always ready to just write it incorrectly. Minus 3y. The x goes to a 1. And then 4y squared just goes to 0. Okay. And then let's get fy. Here x is constant. So now my x cubed goes to 0. And my middle term is minus 3x. The y goes to a 1. And then plus 4y squared becomes 8y. All right. Now, basically then, we have this. So we're going to have here our fx is 3x squared minus 3y, comma, minus 3x plus 8y. So this is our vector. It's actually a vector. This is my fx in the first component, my fy in the second. And we have to dot this, though, with the cosine of pi over 6, comma, sine of pi over 6. Okay? So the cosine of 30 degrees is square root of 3 over 2. Yeah, square root of 3 over 2. Sometimes I've done it enough that I don't, but back in the day, I always had to draw the triangle, you know. Anyway, whatever you do, whatever you have to do. And then the sine of pi over 6 is 1/2. Right. Okay. So we're dotting this with that too. So let's what we want to really actually do then here with this is I want to do one more step with this. I just want to show the dot product. So I'm going to take the square root of 3 over 2 and I'm going to multiply it by the first expression here, 3x squared minus 3y. And then I have a plus. And then I'm going to take the second component, multiply it by the second component, plus 1/2 times minus 3x plus 8y. And I'm not interested in combining any like terms or anything like that. That is fine as an answer, all right? There's enough work to do without doing some extra algebra that I'm not worried about. Okay, now let's say then in addition, let's just say, okay, this is fine, and let's say we're asked to find, same problem, find du, same u, of f applied to 1, 2. So basically then all it's a matter of doing here is plugging in the 1 for the x and the 2 for the y. So that's square root of 3 over 2. So what are we going to have here? We're going to have 3 minus 6. We're going to have what? Minus 3 plus, and then we have 1/2 minus 3 plus 16. So I think that's going to be a 13. All right. And there we have it. I mean, that's good enough for me. So. Okay. All right. Now, what this is leading up to here, is this concept of what's called the gradient vector. Notice up here, let's see here. Let's actually go way back here to the definition of the directional derivative. We had the first component of the unit vector times fx plus the second component of the unit vector times fy, and then I had rewritten it like this, with the fx, fy, dots the ab. This here, this is a vector right here. And of course, this is a vector. This is our unit vector. But that's a vector also. That vector composed of fx, comma, fy is defined as the gradient vector. Okay? So, let me write that down. Gradient vector. And we're going to see it has a very interesting property. The vector, and I'm going to underline that because this is a vector composed of fx, comma, fy, is called the the gradient of f. All right. Now, there's a couple different ways we can denote this. So let me put this as notation. A little bit of shorthand here. We can write grade f like this for shorthand, or we're going to do what I'm going to do most frequently is this. We're going to use an upside down delta, because remember delta is normally like this, right? Where the point is upward, and put the f right after it. We say this as follows: del f. And that's the notation that I'm going to be using most often. Okay. All right. So, del f is equal to the vector with fx in the first part, fy in the second part, or another way we can write that very same vector is fx times the unit vector I plus fy times the unit vector j. Okay. All right. So first thing, we're just going to compute the gradient. That's the first example we're going to have. So example, we're given fxy equal to the sine of x plus e to the xy. Oh, interesting kind of function, combining those two things. And what we're asked to do is find the gradient, del f, and let's find the gradient at a specific xy point, del f 0, 1. All right. So we know that the gradient is the fx, comma the fy. So let's figure those out. Fx, we're going to have y constant for the fx. All right. So let's go up here. Y is constant. All right, so we're going to do the derivative of the sine, which is the cosine. And then we're going to remember y is a constant up there. So what's that partial derivative of exy going to become? Right. Plus y e to the xy. Right. We have to do the chain rule with the xy, and the derivative of xy with respect to x is just the y. So we put our comma there, and now we do our fy where x is constant. Okay. And now in this case, with x being constant, sine of x is just going to go to a 0. And so we're looking at the derivative with respect to y of e to the xy, and that's going to be x e to the xy. Again, with the chain rule. So that's our gradient. All right, now the second part then is we just plug in numbers and simplify. So that's 0, 1. So that's going to give us what here? Okay, 0 for x, 1 for y. Cosine of 0 is 1 plus, okay, 1 for y, 1, let's see, that's going to be 1 e to the 0 times 1 power, and that's e to the 0 power, and that's just 1. Okay, so that's just a 1. And then our second part, what's our second part going to become? Just 0. We got that x in front, x is 0, so that's 0. So the first part is 1 plus 1, so we've got 2 comma 0, and that's the gradient. Why don't we take a 5-minute break now, and we'll continue onward then. How are we doing this morning?
My back was really hurting.
Oh, is that from the accident?
I took the medicine and it's like putting me.
Yeah.
Like that.
So you're on some.
Sorry.
Oh, that's okay. Well, thank you for letting me know that, though, because you know I always think it's me.
No,
I'm.
really
Well, don't be driving a car right now. Okay. Are you going to sue? Didn't the car ram into you?
I mean, I'm not going to sue them, but they're going to sue around.
Absolutely. Well, the insurance. Hope they have insurance, right?
Yeah.
That's good.
Last time I got a massage.
Oh.
But that was for my car, so it's not fault.
Oh. Yeah.
She's
Well, that's. Yeah.
The art, it's like some kind of art healing center, and she's like, she is going to be a class therapist.
Yeah, I have a friend who got all the certifications because they have to learn anatomy and all that. I mean, to get certified, and yeah, so that's nice. She's given a couple of massages. That's always nice. Yeah, she carries her table and her sheets and her oils and all that with her. Yeah. Mm-hmm. Yeah. I thought about that one time because I give a pretty good massage. I really seriously, but then I don't know. I didn't, but I thought about it when I was wondering what to do with the rest of my life. Yeah.
I like getting massages. I don't like it.
I think before we go on to another example here, I want to show this, just kind of a visual thing here. Here, let's go all the way over here. So here we have, in gray here, we've got this surface, and so we have the X, Y, and Z axes. And if you can see here, we have there's an arrow down here in the XY plane, and that's going to be the direction that we're looking at for the directional derivative. Okay, so, and then what you see, if you can see this from the arrow, then we have this vertical plane that is cutting the surface. And then right there we have a point, and we have a line that represents the tangent line. So over here it actually computes the value of the directional derivative, and it says here it's at minus 1.06. So what this program lets us do then is we can rotate the directional arrow, and so basically what happens is that vertical plane then is cutting the surface at different angles as we go along. And then notice here, as we do this, the number value of the directional derivative does change. Now it's minus 1.4. And so we can just keep this, and if you just kind of notice here, keep an eye on the upper right, the directional derivative value is changing as we rotate along different directions. Okay, so here we have negative values. Now it's becoming a little bit less negative. Notice it's flattening out here, okay? And so we're going to be, I imagine we're going to be approaching a directional derivative of 0 as we do this. I think I already passed it up somewhere right here. Yeah, right there. Right there we have a directional derivative of 0. And then we keep rotating. Now it's going to gradually be going up more, and we're going to get bigger positive values for it. Okay, and then we just keep going all the way around. Now, one thing to notice, okay, so these values change for the value of the directional derivative as we circle around. But notice we do reach a point where the value of the directional derivative becomes the largest value. So actually here, I think it's at 1.41, like right, I think right there, because then it goes back down. So somewhere right around here, the value of the directional derivative is the largest. And so what that means is in that direction, if we're moving along the surface in that particular direction, we're increasing the largest, the most. The values of the surface are getting bigger, faster in that direction, okay? As opposed to the direction where they're basically hardly changing at all. And this is where the gradient comes in to play. We're going to see that the gradient gives us the direction in which it increases, the surface increases the fastest. Okay, so that's going to be the value, one of the values of the gradient. Okay. All right. Let's look at this example here. And here it's just finding a directional derivative in a certain direction. So find the directional derivative of fxy equaling x squared y to the third minus 4y. And we're told an xy point, 2, minus 1. So that's our x and that's our y value. But we need a direction, of course, in the direction of v, and there's a reason I'm not putting u here, v equaling 2i plus 5j, or another way of writing that is 2, 5. Now, the reason I didn't put u there is because that's not a unit vector. All right, so that's one thing we'll have to do here is convert that into a unit vector when we calculate our directional derivative. So just want to point that out for right now, not a unit vector. Okay, so of course we need to get the gradient. So let's get del f here. So let's see, that's, of course, that's fx comma fy. So fx, then we're going to be treating y as constant. So I think the first term is going to become, what, 2x y to the third. And then, oh, I'm sorry, how about, well, and the second term is just going to go to 0. All right, so we have that. And then for fy, we're going to treat x as constant. So it looks like 3x squared y squared is what we're going to have. And then now this time x is a constant, so minus 4y is going to become minus 4. Okay. And so we're going to need to find this gradient at 2 comma minus 1. So let's plug in the x and y values here. So let's see. This is going to be 2 times minus 1 to the third power, 3 times 2 squared times minus 1 squared minus 4. All right, be careful. So I think this first component is going to be minus 4. And the second one's going to be, what, 3 fours or 12 minus, it's going to be 8. Okay. Now we have to dot that with the unit vector. Okay. So therefore, to get the directional derivative, we're going to want to get the derivative with the unit for the unit vector. So that's going to be our v vector divided by the magnitude of the v vector. I've got to adjust it to make it a unit vector. So please remember that you have to do that. You have to divide by the magnitude to make it a unit vector. I'm going to put an asterisk by that so you remember, divide by the magnitude to make it a unit vector. All right. So actually, let's figure out what is the magnitude of this vector here. The magnitude of v vector is what? It's going to be it's the square root of the squares, right? So it's the square root of 2 squared plus 5 squared. So that's the square root of 29. Okay. So for this directional derivative then, and this is going to at, let's see, it's at f at 2 comma minus 1. Okay, we've already figured out the first part, the gradient, but we're going to be dotting it now with the following. Let's see. We have to divide both components by the square root of 29. So our components are 2 and 5. So we have 2 divided by the square root of 29, and we have 5 divided by the square root of 29. This now is a unit vector.
Why did we have to get a unit vector?
Because that's how the textbook is defining the directional derivative. This unit vector, where we divide by the square root of 29, it still has the same direction as the original vector. Remember, we can have a vector and where it doesn't have length 1. But if we divide by the magnitude, we can then have a unit vector. And it's going in the same direction. Okay. Right. So that's the deal. It's going to be in the right direction, but we have to divide by the magnitude to make it a unit vector. So here we have a little, okay, so let's just do the arithmetic here with this. We multiply the first two components, minus 4 times 2 over the square root of 29, that's minus 8 over the square root of 29. Then put a plus, and then multiply the second component, that's 8 times 5 is 40 over the square root of 29, and they both have the same denominator. We can just combine them. 40 minus 8 is 32 over the square root of 29. And as far as I'm concerned, you don't need to rationalize the denominator. This would be our answer right here. Okay. So again, we're still going to get the same gradient here for the directional derivative. We get the gradient, but if it is not a unit vector, we have to make it a unit vector in order to get the directional derivative. Okay? All right, let's see here. Okay. Just to give you, we can of course have functions of 3 variables and have a gradient for 3 variables. So I'm just going to show you this. Functions of 3 variables. So f of x, y, and z, and say again we want a unit vector Let's have its components be A, B, and C, all right? Then the directional derivative of our function, and then put the u vector down below, is equal to, it's just an extension of the other definition. It's going to be f with respect to x times the first component of the unit vector plus f with respect to y times the second component plus f with respect to z times the third component. And again, the other way I can represent this is with a dot product. Put my fx, my fy. Now this time I have an fz. And then dot product my unit vector A, B, and C. So it just extends it along one more direction. And again, this is the gradient of the function of 3 variables. So now we have an fz as a third component, the gradient. Okay. Okay. All right. Now I'm going to tell you, give you the theorem that has to do with the gradient giving us the biggest increase in the function. So here's this theorem. I'm going to give you, it has a brief proof to it. I usually don't put the proofs down, but it's kind of a neat little proof and it's not very long, so I want to include this. So if f of, well, let's just say, oops, let me start again. If f, because this can be a function of 2 or 3 variables, if f is a differentiable function of 2, or we can even look at 3 variables, then the maximum value of this directional derivative is, first of all, the magnitude of the gradient. So this absolute value sign, this is the magnitude of the gradient. And this maximum occurs when our unit vector, is in the same direction as the gradient. So this maximum occurs when our unit vector u has the same direction as the gradient. Because remember, that is a vector. Okay. So this theorem tells us two things. It tells us what the biggest increase in the function is going to be. It's going to be the magnitude of the gradient, and it's also telling you the direction that you're going to find that biggest increase, and that direction is also the gradient vector. Okay. So let me just do a brief proof. You can do what you want with this. I think it's kind of nice. So let's look at the directional derivative of our function. And we know that the directional derivative is equal to the gradient dot the unit vector. Okay? Now, remember the dot product. A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. All right? That was one of those formulas we needed to know for the first test. All right. So let's look here. Let me draw a little diagram here. Here's our unit vector that we're doing the directional derivative in that direction. And here is our gradient vector. Remember, it's a vector. In between these two vectors, we can put them tail by tail, and in between, we say that they have an angle, and we'll call the angle theta. Now, the dot product then here is going to be the magnitude of the gradient, so I'm putting the absolute values there, times the magnitude of the unit vector, but that's just going to be a 1 because it's a unit vector, times the cosine of the angle between the two vectors. Okay, this is the value of the directional derivative. Well, we know that this is 1, so this is going to be the magnitude of the gradient times the cosine of the angle between them. So really, the only thing that varies here as we're going around different directions, the only thing that varies is this angle theta as we go different ways. Well, cosine of theta. First of all, we know, what do we know about the cosine? That it can't be bigger than 1 and it can't be less than negative 1. It goes between -1 and 1. So we know the biggest value that this can have is when the cosine of theta is equal to 1. Will give us the max value. Well, what angle is it that gives us a cosine equal to 1? 0, right? Yeah. Theta equal to 0. 0 degrees, 0 radians. That'll give us the biggest value. So we see here, okay, we're going to have the biggest directional derivative value when this angle here is 0, which means that these two vectors, our unit vector is going to be right there on the same direction as our gradient. So therefore, the gradient is going to give us our biggest direction, and so when theta equals 0, therefore the directional derivative is going to equal the magnitude of the gradient. Okay. So you can take that proof or leave it. It's a nice little proof, and I think it's kind of nice. So that is the proof of that. So let's then basically, let's look at something up here, and then we'll do some examples. Right. Okay. What in the world do we have here? All right. So first of all, we have this surface that we see. I'm rotating it around, this gray surface. And let's see if I can get it looking a little bit less lopsided. Sometimes I have trouble with this, and I end up getting it. Oh, see, let me reset it. There we go. That'll do it for me. Okay. X-axis, Y-axis, Z-axis. Now, down here, this little red point right here, this is actually sitting on the XY plane. And notice that there are two arrows coming out from it. I hope you can see that second arrow. This one arrow here that's kind of brownish, that's actually the direction of the directional derivative. Of the gradient. That's the direction of the gradient. All right. And this blue vector is what we're going to vary. Now, what we have up here in the upper right is the actual number value for the directional derivative. So, if we start moving this thing, notice the blue vector is changing. The gradient vector, of course, stays the same. And we get a value up here for our directional derivative. Now, as we're going here this way, notice actually the first thing that I hit here, let's see, is this minus 51, minus 52? Yeah. Okay, right here. Actually here, we're actually doing the directional derivative in the very opposite direction of the gradient. We're pointing 180 degrees opposite it. And let's note the value that we have here. Here we have that the change in our function in that direction is what, a minus 0.52. Oh, you guys can't see what I just wrote. Minus 0.52. All right. And now we just continue moving our direction here, and so we're changing our tangent line up above, and our directional derivative is like 0.22, and now it's starting to go up, 0.36. Our blue line now is starting to get close, approaching the gradient here, so we're getting closer. Notice we're at 0.45 and 0.49. And so we should, now we're at 0.51, we're almost at the gradient, and I managed to get it right there. Okay, now they're laying right on top of each other. So we're looking at the directional derivative in the very same direction as the gradient, and we get now a value, the very opposite value of 0.52. And that's our biggest value that we get for the change in the function. And then we continue along, and now that's going to start to go down, 0.51, 0.50, and it's going to start to go down again as we get away from the gradient. Okay. All right. Okay, let's look at an example here. Fxy is equal to x times e to the y. All right, so let's see what this one has lots of parts to it. Let's find the rate of change of f at the point, put capital P at the point 2, 0, so that's our x and y value, in the direction of the point Q 1/2, 2. Now, this one involves an extra step. here we're told that we're interested in the point at the point 2, 0 on the xy plane. But we want it in the direction of this other point 1/2, 2. So basically, if we just look at an xy plane here, the point we're interested in is 2, 0, so that would be, say, right here. But it's in the direction of this other point, which is what? X is 1/2, y is 2, so it's something like this right here. So we're talking in the direction of, so we're looking at this vector, which is the difference of the q minus the p. This is our q here, this is our p, so we have to get our vector. We have to do a little bit of work to get our vector by subtracting. All right, so we have to get our vector, and we can look at our vector as pq with an arrow above it, and that's going to be the q minus the p. So that's going to be q minus p, so it's going to be 1/2 minus 2, 2 minus 0. So what does that give us? Our vector really is going to be 1/2 minus 2 is what? Minus 3/2. 2 minus 0 is 2. So this is our vector that we're interested in. All right? So we had to do some work to get that. Okay. Now the rate of change, what we're really looking for is the rate of change is going to be the value of our directional derivative. Okay, that's what it's going to be. So to get our directional derivative, first of all, we need to get our del f. So that's the fx and the fy. All right. So let's obtain those. Fx, y is constant. Fy, x is constant. So let's see if we can get all that on the screen there. All right. So let's see, y is constant for, so we're looking at x e to the y, and derivative with respect to x, so that's going to be what? E to the y. The x will go to a 1. We just keep the e to the y. And then the fy, now this time the x is a constant, so the x is a constant, so that's going to stick around, and we're going to x e to the y, because the derivative of e to the y with respect to y is e to the y. So that's x e to the y. Okay. And then we're looking at that, of course, the point that we're interested in is 2, 0. So our gradient at 2, 0 then is going to be, okay, plug in 2 for x and 0 for y. So e to the 0 power is going to be a 1, and then this is going to be 2 times e to the 0 power, which is 2 times 1, or 2. So that's our gradient value, our gradient vector. All right, okay. Now the thing is, we know to get the directional derivative, I have to make sure I'm using a unit vector. This is not a unit vector. If you do the calculations, the square root of the sum of the squares, it doesn't equal 1. So what we have to do then, we're going to look at, we want it to be in that direction, but we need to divide it by the magnitude of that vector. All right? And so we want this directional derivative at that point 2, 0. So it's going to be 1, 2 dot something. Okay. All right. So we have to figure out what's the magnitude of this vector here. We have to do a little number crunching to figure that out. So the magnitude of our given vector direction is what? It's the square root of the squares of each component. Add them together. Unfortunately, we end up with a fraction here, so we have the square root of what? 3 minus 3 over 2 squared is 9 over 4, and then we have a 2 along with it. So, oh yes, 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 thank you, 4. And so we have to combine these. Okay, so we have to try to figure out what we got here by making it into a single fraction. So what are we going to have here? So we're going to use the denominator of 4, right? So we're going to have 9 over 4 plus, multiply it by 4, 16 over 4. And this turns out very nice because we end up with a perfect square in the numerator. So this is the square root of 25, 9 plus 16 over 4. Both are nice perfect squares, so I get the magnitude as 5/2. Okay, all right. So basically what I have to do then is I have to divide my components by 5/2. Now if I'm dividing something by 5/2, okay, I want to try to just do this in the least steps possible. So what am I multiplying it by? Right. We're dividing by 5/2, so let's just jump to the chase quick here and then realize that we're multiplying by 2/5. All right. So I have minus 3/2 times 2/5. That's my first component, and my second component is 2 times the 2/5. So those really become what here? Minus 6/5 and 4/5 is my unit vector that we have. All right, so now it is a matter then of just doing my dot product. Are we okay so far? What did I do now? Oh, wait a minute. Oh, no. Yes, that's right. Thank you. Yes, I'm being sloppy, which is minus 3/5. Oh, this is looking a mess. Minus 3/5, 4/5. Yes. All right. Thanks for keeping me honest. And of course, that's a unit vector. All right, so we're dotting it with that. So we have our directional derivative in the direction of our unit vector of our function at 2, 0. Then it's just going to be the dot product of 1, 2 dot minus 3/5, 4/5. And so that's going to be 1 times minus 3/5 plus 2 times 4, 8/5. And, whoa, you know what? This is going to give us 5/5, so it's equal to 1. Okay. All right. So the deal with this problem is we had a couple things we had to do first. We had to figure out the direction that we're doing, and then we had to divide by its magnitude to get a unit vector. All right, so that's the first question that they were asking for. So that's our rate of change that we're looking for, whatever the dimensions are of that. Now let's look at another question here, part B here. In what direction, now the questions get easier. In what direction does our function f have the maximum rate of change? Okay. Well, along what direction, moving towards what direction do we have the biggest rate of change? Starts with the letter G. Along the gradient, right. So it's going to be the gradient at the point 2 comma 0, well, we already, in the first part of the problem, we did all the hard work. We found the gradient, that del f at 2 comma 0 is equal to the direction 1 comma 2. So therefore, that's our answer. That's the direction of the maximum change. All right. And let's see, part C, I think, is another kind of gimme. Let's see what the question I'm going to ask. What is what is the maximum rate of change along the gradient direction? Let's see, what did the theorem tell us that the maximum rate of change, the actual change itself? Let's see, where is that theorem here? Ah, yeah. Yeah, the magnitude of the gradient. That's going to give us our maximum rate of change. So the answer is, of course, the magnitude of the gradient okay, but we already figured out our gradient is 1 comma 2. So the magnitude then is going to be the square root of 1 squared plus 2 squared, which is the square root of 5. And that's the biggest rate of change we're going to have. Okay. All right. So that's kind of a comprehensive problem using how we define the directional derivative and using that theorem. So you can be assured that come a couple of weeks you're probably going to have something like this. All right. But we'll get closer to that bridge and deal with it when we get a little bit closer. All right. Well, let me just get started on. So that is basically that's the first. There are like two kind of big topics in this section. And the first one was this thing about the directional derivative and the gradient. All right. The third topic that this section wants to deal with are tangent planes. And Jenna's saying, I am so glad we're getting back to tangent planes because I've been missing that, right? Tangent planes to what are called level surfaces. Say, oh my goodness. All right. Now, it was a couple days ago, a couple classes ago where we had this formula. So that's why I'm putting recall. If our surface is given like this, if our surface is z equals a function of x and y, in other words, z is isolated all by itself on one side, we have that the equation of the tangent plane, then the equation of the tangent plane at point x naught, y naught, z naught on the surface is the following. Z minus z naught equals fx at x naught, y naught times x minus x naught plus then fy of x naught, y naught times y minus y naught, okay? And where this is linear in x and y. Linear in x and y. All right. So let me put an asterisk by that again because that's something that I want you guys to remember. All right, that's if we have a surface that's defined like that. However, life isn't always so easy where we have surfaces that are nicely defined where Z is all by itself on one side. Okay. So sometimes, and it probably in reality, it's probably more often than not, but I'll put sometimes we can't isolate Z like that. Z like that. And let me just give you an example. X cubed plus Y cubed plus Z cubed plus 1 equals X plus Y plus Z plus 1, all in parentheses, cubed. That's kind of a clever little thing here. Notice that on the left side, we have cubes after all the individual terms. And then on the right side, we just have all those individual terms in parentheses, and then we cube them. All right. This actually gives us a surface. We have a surface here that, notice there's no way algebraically we can isolate, we can try to do some clever algebra and isolate just Z on one side. That ain't going to happen, all right? So this is basically you can do a graph of this. In fact, I did a graph of this using, believe me, I didn't graph it myself. I plugged it into Maple. Where is it? Where? I'll be very upset if I don't find this crazy little graph. Ah, here it is. So here's the graph of this surface. Unfortunately, I can't twirl this thing around like I could if I actually had Maple up here. Because on the back side of this thing has another thing going out. So I don't know, it almost looks like some kind of, like you have some kind of joint that's combining where we're going in this direction, and this direction. Anyway, this is the graph of it, of that. So, and this is the surface. It's hollow in here. The surface is the layer there on top of it, okay? All right. So notice we, here, I'm going to keep this up here on the screen. We're almost done here. So notice we can't isolate Z on one side. But there's another way I can write this thing. Let's just move all the variable stuff on one side and put that one that's sticking there, put that over on the other side. So let's rewrite it like this. Okay, X cubed plus Y cubed plus Z cubed. Now I'm going to move that 1 over to the other side, but I'm going to take this whole term here and put it over on the left side, minus parentheses X plus Y plus Z plus 1 cubed equals, and then I'm putting that 1 over onto the other side. Okay. So notice what we have here on the left side. We have a function that has the variables x, y, and z. So I can write this as some capital F of x, y, and z equal to -1. All right. That is also an equation. This is also an equation of that surface that I put up on the screen of our surface. Okay. So, what we're going to look at here is in general, let some capital F of the variables x, y, and z equal to some constant k, constant. And let this be the equation of our surface. All right. What we're then going to get from this is we're going to derive the equation of the tangent plane to this surface. Okay. This is not going to be a nice, it's actually a very elegant kind of, elegant is another mathematical term that you hear where things work out very prettily, nicely, okay? But it's not going to look like the one equation of the tangent plane that we had before. It's going to have a different look to it. The last thing I want to point out here is this. Look at this equation right up here. We have variables on one side, but on the other side, all we have is a constant. We can look at this as a level surface of the function capital F. In other words, this is where this big function capital F only equals this one constant value. So this is a quote-unquote level surface of our function capital F, i.e. where it equals the constant k. Okay. All right. So we'll have to just stop here and getting started on anything else, then I'm just going to leave you hanging with a sentence that's we'll just start it all after this next time then.